Good day, everybody. This is Chris with the Ancient Scholar, and we are finally going to get to the point of this whole discussion here. We're going to take off from where we talked about charge selective membrane and ion trapping, and we knew that aspirin, um, its ability to dissociate or ionize is affected by pH, the pH of the environment that aspirin is in. And we saw that qualitatively, at least in the last video. So now what I'm going to do is I'm going to say that I have a patient who is overdosed on aspirin, or ASA, as we often abbreviate that. And we know that aspirin has lots of negative effects associated with it. It affects certainly the central nervous system. It can cause profound neurological problems in addition to affecting the hypothalamus and thermal regulation. It can cause hyperpyrexia, or really high fevers. Could cause rather profound electrolyte and metabolic imbalances, particularly good at causing a metabolic acidosis. It is an acid. It can also affect other organ systems such as the liver and the kidneys. We talk about the initial management of any overdose really revolves around making sure that the patient has an airway and that the airway is patent, and that they're not throwing up, and that it's full of emesis, and that it's secure and we're able to maintain it, and that we're breathing effectively and we're getting air in and out of the lungs, and we're able to get oxygen where it needs to go, carbon dioxide out of the body, and that it's a circulatory status, a circulatory system. There's enough fluid in it. The heart, its contractility is optimized. The blood vessels, how they are dilated or expanded, is optimized. And we call this the ABCs: airway, breathing, and circulation. And once we get the ABC secured, or reasonably secured, and we can work on administering certain medications to optimize the ABCs, antidotes. Obviously, lab testing is going to be important. We're going to want to look at what's known as a CMP, or a complete metabolic panel. See how the fluid and electrolyte status is doing. We'll do an arterial blood gas to look at the acid-base balance of the body, and see how well we're oxygenating and ventilating. And obviously, we'll run some tests and look at the levels. Look for toxins in the body. Aspirin, or ASA, acetylsalicylic acid, is a common thing that we look for in people that are suspected of overdose, in addition to things like Tylenol and tricyclic antidepressants. These are things that we can fairly detect levels of fairly easily in a lot of labs, even in smaller hospitals. So a lot of things go into it. But what I want to talk about is a treatment modality. Somebody who has fairly significant overdose of aspirin, and that treatment modality is known as urinary alkalinization. And I'll just abbreviate that as UA, not urinalysis, but urinary alkalinization. I am going to administer a medication called sodium bicarbonate, and that's Na, all right, HCO3, and of course it's in an intravenous form. I administer it intravenously, and in an aqueous environment, this medication then dissociates into sodium ions and into bicarbonate ions. And we know that bicarbonate, HCO3 negative, is a base. Bicarbonate is able to accept protons, and therefore it meets the standard Bronsted-Lowry definition of being a base. So administering sodium bicarbonate will increase the pH within the body. Okay, it'll increase the pH. It will make our body more alkalotic. Well, how does that help with aspirin overdose? Well, what I want to do is I want to look at the urine. Okay, so what I'm going to do is I'm going to draw a little table here. And I am going to have a normal urinary pH. So let's say that we have normal urinary pH over here. Okay, so normal, okay, use your imagination. just that says normal. And then I'm going to have properly alkalized urine, or urinary alkalinization, with sodium bicarbonate over here. Okay, so here's my table. All right, normal and urinary alkalinization. Okay, and we can compare and contrast these. So normal pH of the urine is approximately, this varies fairly, it can vary fairly significantly, but it's approximately 7.0, more or less neutral, but a bit more acidic when compared to the plasma of the blood, which we learned earlier was about 7.4. So, more or less neutral, but acidic when compared to the body. This can change. This can vary quite a bit, depending on diet and whatnot. But let's just say that it's more or less around 7. Okay, and then with proper urinary alkalinization therapy, I'm going to have a urinary pH of, I'm shooting for approximately 7.5. All right. Now, this may not seem like a significant difference from 7.0 to 7.5, but we know that with every point, because we're talking about a logarithmic scale, a base 10, every point is going to be an order of magnitude, or 10 times. So 7.5, that's 5 orders of magnitude more alkaline than 7.0. So this is actually significantly more alkaline than this. Simply because we're talking about a base 10, okay? That's what this is actually representing, our pH. So keep that in the back of your mind. Okay, so now what I'm going to do is, remember we talked about how in an alkaline, in the acidic environment of the stomach, aspirin tended to stay, more aspirin was in its non-ionized form. It was able to pass through membranes fairly easily. Whereas in the alkaline environment of the blood, aspirin dissociated into its ionic form, its acidic, its acid conjugate base. Once in the blood, of course, it was kind of trapped there by the charge selective membrane. We call that ion trapping. So what I'm going to do now is I'm going to dive into kind of the quantitative basis of that, and it's going to go back to the pKa. Remember, that's just the log base 10 of the Ka value. And the pKa of aspirin is about 3.48, but I'm just going to round it for simplicity's sake to 3.5. The pKa of aspirin is at 3.5. Now, an interesting thing about pKa is that if I were to take that aspirin, and if that aspirin was dissolved in an aqueous environment that had a pH of 3.5, okay? So I put it, maybe a mole of aspirin into a liter of solution that had a pH of 3.5. At a pKa of 3.5, I would actually have 50% of that aspirin in its ionized form and 50% in its deionized form, or its non-ionized form, rather. So I would have a 1-to-1 ratio, 50% here, 50% there. So 50% in its ionized form, so the ion, and non-ionized form. So that means that at a pH of 3.5, 50% of the aspirin would be able to penetrate membranes, the non-ionized form over here, and the other 50% of that aspirin would not be able to, would be on its ionized form. Okay, that's an interesting thing about pKa. Any weak acid, whatever the pKa of that weak acid is, at that pH, the pH of the pKa, it'll be 50% disassociated. So if the pKa of something was 4, that would, and you were to dissolve it in a solution that had a pH of 4, you'd have about a 50% ionization. Okay, fair enough. So what I'm going to do now is I am going to look at an equation that we use quite a bit in respiratory therapy, actually. We use it to predict or to calculate the pHs of blood plasma when we don't know the pH, but we do know the bicarbonate and carbon dioxide levels. And that equation is known as the Bronsted-Lowry, or oops, not the Bronsted-Lowry, what am I thinking? It's the Henderson-Hasselbalch, excuse me. It's the Henderson-Hasselbalch equation. Henderson, D-E-R-S-O-N, I'm going to just put some dots there. Hasselbalch, I believe it's spelled H-A-S-S-E-L-B-A-L-C-H. Henderson-Hasselbalch, I believe, is a proper spelling. There may be some chemistry whizzes that'll troll my comment section and remind me of the proper spelling if that's incorrect. But be that as it may, there it is. I believe that's how it's spelled. The Henderson-Hasselbalch equation takes on the general form of the following. It says pH equals pKa. So pH equals pKa plus the logarithm, okay, of my substance, whatever I'm looking at, in its acidic form over, remember brackets are molar, we're talking about the molar concentration, to its deionized form, HA. Okay, so that's the general form of the Henderson-Hasselbalch equation. In respiratory therapy, if you do a good class, if you have good instructors to take you through it, you generally know the A and HA and the pKa value, which is generally 6.1 in blood plasma, and you solve for the pH. But here, what I'm going to do is I am going to solve. I know the pH. I'm going to look at normal urine and alkalized urine. I know the pH, but I don't know the ratio here of ionized to deionized, aspirin in this case. So I'm going to set the formula up like the following. I'm going to start with normal urine. I'm going to put the normal pH, 7, equals pKa, pK of aspirin being 3.5. Okay, plus the log. And since I don't know this ratio here, I'm just going to go log, and we're going to always assume that I'm talking about log base 10. And I'm just going to make that whole thing x. This whole thing up here, I'm going to make x since I don't know it. All right, so 7 equals 3.5 plus the logarithm base 10 of x. All right, well, I can solve this fairly easily. How about I just take this 3.5 here and come over here and subtract that from 7, okay? So 7, 6, 5, 4, that should give me about 3.5, all right? So 7 subtract 3.5, 3.5 equals the log base 10 again of x, okay? Put the little 10 there. All right, so what this is telling me is that the logarithm of x, the log base 10, not logarithm, the log base 10 of x is 3.5, right? What does that mean? Well, whatever the log of something, log base 10 of what equals 3.5? Well, in this case, it's going to be approximately 3,600, I believe it's about 3,100 actually, 3,162, okay? So more or less, approximately 3,162, okay? So 3,162 over 1 is the solution to this ratio here. So what that tells me is that in normal urine, with a pH of 7, I have 3,162 parts of ionized aspirin to 1 part of non-ionized aspirin, okay? So if I have, if we're looking just a basic, I have in the tubule here, the kidney tubule, and this is the urine that's being produced. Okay, the urine in here, that's telling me that the aspirin that is in this tubule here, okay, 3,162 parts of that aspirin per. So for every part of that aspirin that is non-ionized, there will be 3,162 parts that are ionized. Okay, so this non-ionized part can pass through the membrane and back into the body and won't necessarily be eliminated, whereas the rest of this will. That kind of seems like a lot, but remember, we have somebody who's in really bad shape, and we need to get as much aspirin eliminated as possible. And so what I'm going to do now is I'm going to show you what happens when I alkalize the urine, okay? And we've got the formula to back it up here. So let's just see what happens when we alkalize the urine. Does something change? Well, let's go ahead and do that. Let's go ahead and plug in. We'll run the equation again here. All right. So now I have alkalized the urine to 7.5. So the pH instead of 7 equals 7.5 equals the pKa of aspirin, which is still 3.5 plus the log base 10 plus the log base 10, and I'm going to make that x again. Okay? All right, so same thing. It's just basic algebra here. Don't have to do anything crazy. I'll take 3.5, subtract that from 7.5, okay? And what does that give me? Well, 7.5, 7, 6, 5, 4, let's see, 7.5, subtract 3.5. Let me do that math pretty easily. 1.5, 3.5, I'll just cancel out. 4. It leaves us with 4. How about that? So now I'm going to put 4 equals, okay, the log base 10 of x. Now this may not seem like a big difference, right? I think the last one was 3.5 and this one is 4. Remember, we're dealing with a logarithm, however. So 4 is actually, so the log of what? Log of what? X is what? Log of what equals 4? Well, that's significantly larger, actually. The log of 10,000 equals 4, okay? So I take the logarithm of 10,000, that equals 4. So the answer to this, when I have my urinary pH increased to 7.5, is a ratio of 10,000 to 1. So that is significantly larger. So if we go up here under alkalized urine, I now have a ratio of 10,000, okay, 10,000 ionized, okay, 10,000 ionized, ION, 10,000 ionized parts of aspirin to 1 part non-ionized. Okay, so this is like, at this point, 99.9999, 3 nines, I believe, % of my aspirin is in its ionized form. So here, I'll just draw an arrow, is what we have here. I have 3,000 parts ionized to 1 part non-ionized. Now, by increasing the pH of the urine, I have 10,000 parts of ionized aspirin to 1 part non-ionized. And what does that mean? That means that these 10,000 parts are not going to be able to effectively cross the membrane back into the body, right? It's going to be trapped. I'm going to have ion trapping in the urine, and then assuming that my potassium levels are okay and that I'm hydrated, my kidneys are working, assuming that, I will be able to flush that aspirin out, and I will be able to eliminate significantly more aspirin if my urinary pH is 7.5 versus my urinary pH of being 7. So hopefully that made sense, and I hope you guys enjoyed this series of videos. I know this one had a little bit of math on it, but I just thought it's really interesting that I can take some of these basic concepts that I learned in my chemistry and biology and or microbiology and anatomy and physiology, some of my science courses that I've taken years ago, and I'm now looking at them in a brand new light, and I'm using them in very different ways in just a broad applications that kind of come out of these really fundamental concepts. And they're not very easy intuitively either to understand, particularly acid-base. But boy, when you start looking at things like toxicology and other biological processes, it really does kind of bring home, to me at least, this concept that, wow, I'm really able to make deep predictions about the world and do it in a way, and in this case with toxicology, in a way that can potentially help people. So that's really interesting, and it's just I'm so excited that I'm able to do these different things and do these calculations and make these really exciting predictions. And I just kind of wanted to share that with my audience or anybody who finds this as interesting as I do. Okay, guys, as always, thanks for hanging in there.